I mean, there's some department issue to take care. 所以可以了吗 ？OK. Yeah, talk about that. I mean, just curious, like for you guys, like I mean, because I just heard like one case, like interesting student. Okay, he, what should I say? Like he has to perform very well. If he doesn't perform well enough, he just give up everything. 你知道，要不然就是表现很好，要不然的话就完全连考试都不去考，就是 something like that, you know. Yeah, for me, I kind of feel like you know, this is kind of like a destructive like personality, you know. 有点危险啊，对 ，a little bit dangerous. I think, okay. I mean, if you, I mean, in your career, in your you know, in your life, like there are always like challenges, obstacles. You know, sometimes you just have bad lucks. You know, some people treat you badly. You know, things happen. You know, but do not give up. You know, even when your performance is not, you know, at the top, like by other people's opinion, you know, it's really like a, you know, the at the end, like, you know, it's you yourself to evaluate your own performance. Don't be judged by somebody else. Okay, that's my suggestion. Okay, 就是你人生里面一定会有挫折，一定会有一些这个怎么讲？就是说表现不好的时候，你不可能我们不可能是永远是人生胜利组哦。人生胜利组这个机会太小了，就是对，拿我自己当例子好了。我在高中以前，我都觉得说，我考高中也失利嘛。我那时候去中正嘛，中正在台北也不算说那个，至少不是前3志愿，对不对？对，那时候我那时候中正第4志愿啊，现在好像中正变得更后面一些，对啊，那所以我考高中也失利。那到大学的时候，但我在高中表现的还不错。那到大学以后的时候，其实因为你知道台大数学系是一堆那个资优生嘛 ，a lot of like talented students。那个在里面的时候，就是因为我以前我读数学系，就是因为我觉得我数学念得还不错嘛，所以我去读数学系。那去那边才发觉说，人家我在大学想要念的数学，有很多人在国中就念完了。OK， 国中就念完了。他们去那边是复习，我们去那边是学新东西，他们去那边是复习。所以我一些同学，那考试的时候啊，就是考试前半个钟头跑来问我们同学说：“哎，今天考到哪边呢？”然后就看到说跟他讲说：“哎，考到哪边？”他就坐下来开始翻，就翻过一遍。然后考完了，我们大家都因为老师出的题目都超难，我们大家都考20-30分，那个学生过来翻半个钟头书的，考80-90分。那你怎么办？你如果碰到像这种事情，你怎么办？你觉得说人生就完蛋了吗？对，我还是 manage 想办法把它过了嘛，对不对？但是成绩不够好，但是你知道自己有学到东西 ，that's the most important thing that you know。所以你自己要对自己知道怎么讲，就是说你要自己要对自己也负责啦，就也要对自己就是说不要那么容易 give up。就算是别人觉得说你表现不好，并不代表你自己是这样的人。OK， 我觉得这个很重要哦。对，所以花了一点时间跟大家讲一下这个。好 ，Anyway， 那这个 chapter，OK，this is the last example in this chapter, and then next we are going to move on to the next chapter actually. OK， So it's, this question is the VLSI layout, okay? So the problem is we want to embed a complete binary tree with n leaves in a grid using minimum area. So the key points using the minimum area. So you will be able to find out, for example, here. So this is like a, if you try to, what should I say, like this is binary tree, right? So we try to embed this binary tree like in one dimension. Okay, so it grows like on this like x in width. It grows in width. Of course, like when it grows in width, the height also grows a little bit, but not much, right? So for example, okay, you can see this binary tree. This is like this is also like one complete binary tree, right? And if you want to grow, so you expand, you put like another copy here, and just increase one layer, right? So you could do exactly the same. Okay, copy this whole thing to the on the right hand side, and then add one layer again. Okay, so you can keep growing this binary tree with n leaves. Okay, in a grid. Okay, using this manner. Okay, just keep expanding it like in one direction. Okay, so if this is the case, let's consider the height and the width, because like the area, because we need to consider the area, right? The area will be the height multiplied by the width, right? So let's see like Hn and the Wn. Okay. So your Hn, okay, will be h of n divided by 2 plus theta 1. Okay, what does that mean? Okay, because every time, okay, if you increase, okay, I mean, if this is Hn, like it will be the half of it. Here we are considering the height, right? So it will be half of the subtree, the binary trees, half of the binary complete binary tree. Okay, and the height of that plus one additional level, right? As I said, like we just need to connect these two, subtrees together to form a larger binary complete binary tree. So it's like h n divided by 2 plus theta 1. Okay, so we know like if you are given this recursive recurrence relation, then your h of n is going to be theta log n, right? Because this format is exactly the same as binary search, right? In the binary search, the order is log n, right? So that's our height. How about the width? The width, okay, it will be width of n equal to, because we need to accommodate two of them. The width will be this width plus this width. Okay, so it will be 2 times of the width of like n divided by 2. Okay, plus we need a little bit additional space. Okay, for the width, to combine these two subtrees. So it could be something like that. And in this case, the A is 2, B is 2, and it will give you, so log 2, it will be like the order is 1. So it will be theta. And okay, this is like the first case in a master theorem. Okay, so because the height grows in log and the width grows linearly, so you can see that the area will be, it grows, in n log n. It should be very easy to understand, right? Okay. So this is like the case, okay, if you grow the tree in one direction, okay, remember, 你们在做那个，我知道我们不是做硬体的啦。I mean, in our department we are computer science, so we are not really into like that much IC design. Okay, but I think like you guys, after all, like if you are in this area, we are in the similar area of like electrical engineering. So, like like for example, like in IC design, okay, they now like try to build like IC in multi-dimension, right? 那他们在设计 IC 的时候，他们 IC 事实上是3D 的，对不对？所以我们这个就比较像是一个1D 的 case， 一维的 case。为什么我讲这样子 ？Let's consider this one. This is like in this case we are growing this complete binary tree in 2 different directions, right? In 2 different. So in this case, well, it's almost square, right? So both the width and the height will be considered like just Ln, okay. So you can see that, okay. So this is a subtree. Okay, this is subtree. And then, if you increase, okay, every time increase by like combining 4 of these. So, if you try to take that into consideration, each of these is like Ln divided by 4, right? Because what is n? N is number of leaf nodes, right? Number of leaf nodes. Okay, so here, okay, if we consider this area, the number of leaf nodes in this area is 1/4 of the number of leaf nodes in the whole area, right? So that's why this is Ln divided by 4. Okay, so the length of n divided by 4 is this much. So this is like constant amount. This is Ln divided by 4. So the Ln actually can be represented as like 2 times Ln divided by 4 plus theta 1. And because A is 2, B is 4, and the order here is 2 to the power of 0. So we know like again this is log 2 4/2. Sorry, log 4/2. So it's 0.5, or like it's the first case is like n square root of n. Okay, first case. In the master theorem. Okay, so if the one side grows like in square root of n, because the area is like a square of n, right? Square of the length. So we know like area grows, linearly. Okay, we call this thing as H-tree embedding. Okay, in VLSI design. So this is a 2-dimensional, right? Because we grow both width and height, right? We could grow this binary tree, complete binary tree, in 3-dimensional. Okay, you can see that. Okay, if we grow this tree in 2 dimensions, the area grows in n log n. If you grow this binary tree, okay, in 2 dimensions, the area grows linearly. If you want to save because remember, like every time you want to, in like IC design or like TSMC, they always talk about like how small the IC chips are, right? 就是你的那个 IC 区别要设计越小越好。也就是说，那个 area 我们希望它越小越好。那但是我们又希望它的那个因为那个 leaf node 哦 ，leaf nodes are the place that we can connect device, right? 所以我们希望能够连接越多的 device， 用越小的 area 连接越多的 device。所以呢 ，so you know if it's like a one-dimensional, okay, it's n log n, the area grows n log in n log n. If it's two-dimensional, the area grows in theta n, so it's a linear growth. So if we want to save even more area, what do? You go, 3-dimension, right? You go 3-dimension. So this show you like the rational why the IC design, okay, try to go higher dimensional. Okay? Okay, so just want to give you an idea. Okay, so the conclusion, okay, the take-home message from this chapter, okay, divide and conquer just one of several powerful techniques for algorithm design. Okay, in fact, okay, we are going to talk about divide and conquer in the next chapter as well. Okay, so divide and conquer algorithms can be analyzed using recurrences and the methods. Okay, so yeah, we talked about master method or master theorem. Okay, last week. So this is like a good there's a very good applications for analyzing divide and conquer algorithms. Okay, and divide and conquer strategy often leads to efficient algorithms. It's not always like that, okay? But with careful design, divide and conquer strategy usually I can say maybe more than 90% will give you efficient algorithm design, okay? So this is what we learned from this chapter, okay? And in fact, okay, we are not done with divide and conquer. Okay, next chapter we are going to talk about the quicksort. So, I mean, quicksort is also one of the famous divide and conquer algorithm, but it's just a little bit more complicated. And okay, yeah. So. Yeah, of course, we won't be able to cover the whole chapter today, okay, because quicksort, as I told you, okay, it's not just, we are not just going to cover quicksort. We are going to talk about, a randomized version of the quicksort, in this case, in this class, as I say, there are different algorithm design principle, okay, that we will consider. Divide and conquer is one of them. Randomized algorithm is another important algorithm design paradigm, okay, and this chapter, the chapter 4, lecture 4, okay, will be the first time you encountered the randomized algorithm, okay, and with that, you will see how the randomized algorithm helps to reduce the complexity, the time complexity. Of course, I mean, it's probably not going to be covered today. We are going to finish the whole chapter, the whole lecture, like, next week. Next week, okay? Just want to give you an idea, okay? So, well, let's take 10 minutes break. When we come back, we'll start like, talk about like a quick sort, okay?